So looking at probability. First thing, if we're going to talk about it, we need to know what it is. So when we're looking at a probability, it's just the likelihood of a random behavior occurring, or the likelihood that an event occurs. You guys have seen probabilities many times. You probably see them as percents a lot of time. Think about the weather. There's a 30% chance of rain today. That's a probability. Or we might see it as a decimal or a fraction. There's a 3 in 5 chance that something happens. Okay, so we can see them represented in different ways. When we are looking at this, a lot of times I'm going to reference the law of large numbers. And it says that as the number of trials increase, the closer the probability gets to the expected probability. Okay, what that means is if I took a dice, okay, what is the probability that I roll a 3? 1 in 6. There is 1 3 out of the 6 sides of this dice. Okay, but does that mean if I roll this dice 6 times, I will get 1 3? No. So the expected probability is 1 in 6, but that may not be how it actually turns out. However, if I rolled the dice 300 times, do you think I would be more likely to have 1 in 6 as a 3? Most likely, yes. So law of large numbers tells us the more trials we have, the closer our probability will get to what we expect. All right. A couple of things that a couple other terms you'll hear me using. So a sample space is a collection of all the possible outcomes. So if I'm rolling a dice, my sample space, that's everything that could happen. So what are my possible outcomes? 1, 2, 3, 4, 5, 6. Okay, that's my sample space. An event is any collection of outcomes. So it might be, so with my dice, so if I'm rolling my sample space, an actual event might be, I'm going to roll this 3 times, and let's see what I get. I'm looking for just a regular one. The one I had out had trig functions on it. That's probably not real helpful. Okay, so if I actually roll it 3 times, I got a 1, a 5, and a 4. So my event might be 1, 5, 4. One particular scenario that I got. Do you guys understand all these probabilities so far? What we're talking about term-wise? So let's take a look at an example. So let's say our probability experiment, we are going to look at having 2 children. I want to identify the outcomes in terms of gender. So what are the possible options? We know that a child is either a boy or a girl. So those are the potential outcomes. Either boy or girl. Sample space is a listing of all possible outcomes. So my sample space, when I look at this, it could be that both children are boys. It could be that both children are girls. It could be that the first is a boy and the second is a girl. Is it different to say girl than boy? If you're thinking in terms of the oldest and youngest, the oldest child being a boy and the next one being a girl is different than the oldest one being a girl and the next one being a boy. So those are all my possible outcomes. That's my sample space. All right, now, can you tell me which of those would be the event have 1 boy? So which which of these four outcomes?
Either the third or fourth.
So having one boy could be boy girl or girl boy. What's the probability of having two girls? 1 in 4. One of those outcomes had two girls. There were 4 total outcomes. What's the probability of having one girl and one boy? 2 out of the 4, which reduces to 1/2. So we always put our probability in lowest terms. Yes. Same if you did a percent, 50%. So probability rules. Probability always has to be between 0 and 1 if you think of it as percents. We're not going to have a negative percent. You can't have a percent higher than 100 in this scenario. The sum of the probabilities of all the outcomes have to equal 1. So when I add up the probability of each different option, it has to be 1. The probability of of 2 boys in the previous example would have been 1 in 4. The probability of 2 girls was 1 in 4. The probability of 1 girl and 1 boy was 1/2. And if you do 1/4 plus 1/4 plus 1/2, we get 1. So all the probabilities should always add up to 1. All right. A couple more terms and then we'll look at an example. A probability model is basically listing the possible outcomes and each probability. So for this probability model, we can do the outcome and the probability. So this was 2 boys. This was 2 girls. And this was 1 boy, 1 girl. So it's like making a table of what could happen in probability with each of those. And at the end, all those probabilities should add up to 1. If an event is impossible, that means it cannot happen. So in my probability experiment of the 2 children, would it be possible for me to have 3 girls? No. So if something cannot happen, it has a probability of 0. If it is certain, so a probability of 100% or 1. We are also going to talk about unusual a lot of times. So unusual means it can happen. What? So unusual means it can happen, but it's not likely. Okay, could it snow at the softball game today? It could. Is that a very likely thing? No. So it's not impossible. We could have a massive cold front come through and dump some snow on the softball field. But it's probably not going to happen. That's unusual. Typically, unusual is defined as less than 5%. So probability of less than 5% is considered unusual. Let's look at an example. So suppose a bag of 100 M&Ms contains 12 brown, 15 yellow, 12 red, 23 orange, 23 blue, and 15 green. Create the probability model. When I say probability model, what am I wanting? The table. So we're basically making ourselves a table. My outcome, in this case, that's the color and the probability. I don't care if you do them as fractions or decimals, but if you do fractions, make sure they are in lowest terms. So, brown, how many total M&Ms are there?
12%.
So So for your brown, it's like 12 out of 100. So can we just do the decimal 0.12? In general, if it's not decimals that round nicely, I would prefer you leave it as a fraction because we do want to be able to check these probabilities. So if it was like 0.3 repeating, I would rather you say 1/3 instead of saying 1/3.
Could we put it in percent?
You technically could, usually we don't, but if you do the percent, you just make sure you put the percent symbol by each one. So yellow, we had 15 yellow, so 15 out of 100, 0.15. 12 red, so 12 over 100 is 0.12. 23 orange, 0.23, and 15 red. All right, does everyone know where these decimals came from? And then quick check, how do I verify that it's a probability model? Yep, there's really two requirements. Every one of these has to be between 0 and 1. Are they? Yes, and it has to add up to 1 total. Does it? Okay, so we know we caught them all. This is a good check if you are actually going through some data and counting how many of each color. That way, if you're checking that it adds to 1, you'll make sure you don't miss anything. Okay. I kind of condensed some things in your notes so I could print it on one piece of paper, but the first one we're talking about, there's different ways of calculating probability. The empirical approach is what we just did. So we find the probability by taking the number of times it's observed, dividing by the number of repetitions of the experiment. We took the number of brown M&Ms divided by all of the total M&Ms. So this is our straightforward, probably what you think of when you think finding probabilities. So if we take a look at this one. An insurance agent insures 182 teenage drivers. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on this, what is the probability that a teen will file a claim? So how would we find that probability? We're finding the probability they had a claim, so we would do the number that had a claim divided by the total number of drivers. So different options. Since this isn't the strict probability model, if you wanted to give me a decimal, you could. As a fraction, this is not a nice one. You get 12 over 91, so you could say that. If you give me the decimals, then please keep at least 4, so it's not too far off. So we have a probability of 12 out of 91, or about 0.139. So there's about a 13% chance that our teenager would file a claim based on our experience. So empirical is basically looking at an actual scenario that happened and finding the probability of that. Let's do another one. Have you guys ever played Pass the Pigs? It's a really fun game. We might have to play it one day. So you roll these pigs instead of dice, and depending on how they land, you get different points. We're gonna have to play Pass the Pigs one day. I love that game. But okay, so a class of 52 students is playing Pass the Pigs. Use the results of the experiment to build a probability model for the way the pig lands. Okay, so these are all the different outcomes. So the pig has 2 sides, and one side has a dot and one doesn't, and then they could land on their feet, or on their snout, or on their back, all these different ways. So we look at this, we have the outcome, and we have the frequency. What do I mean by frequency? The number of times we saw that. Okay, so for our probability model, we're basically looking at the outcome and the probability of each. I'm just going to add it onto this table instead of making a whole new one. So how do we find the probability? Yep. So we need to know how many trials we had. So we'll add all these up. So how do we find each of our probabilities? So your frequency divided by your total outcomes. These are not going to come out nice at all. So let's just do the 4 decimal places because we have a pretty big sample here. Will this add up to exactly 1? Maybe, but maybe not because I am rounding a little bit. It does? Oh, look at us. We're good. So, quick check, verify every probability is between 0 and 1. They add up to 1 in this scenario. If you have a little rounding error, it might be slightly more or less. But that is our probability model. Everybody understands where that came from? Alright, so estimate the probability that a thrown pig lands on the side with the dot. If you have a probability model, this is pretty simple. We just have to look side with dot. What was the probability? 0.3285. If you want to give percent, that's fine. But make sure you put the percent symbol if you do that. Would it be unusual to throw a leaning jowler? What did we define as unusual? Less than 5%. So this one, that's a 0.8%. Is that unusual?
Yes.
Yes. Anything less than 5% we would call unusual. Any questions on that? Okay, second type of probability is classical. So if you go back to that one slide where I gave the definition of the empirical, I also put the classical on that. So classical is when we have n equally likely outcomes, and the number of ways an event can occur is m, then we can find our probability strictly by dividing. So we have, not what I meant to do at all. I know. Okay, so we have n total outcomes, we have m ways that it can occur, so we just divide. Number, your outcome divided by the number of different options. This is like our rolling a dice. Okay, when we said the probability was 1 out of 6 of rolling a 3, that wasn't because you watched me roll the dice 6 times and we got 1 3 out of that. That was because we knew there were 6 outcomes and one of those would be a 3. If I'm flipping a coin, what's the probability of flipping a heads? 50%, 1 out of 2. Okay, you didn't have to see me flip a coin to do that. So empirical is based off what you have observed happening. So it might be, I flipped my coin 10 times and I got 8 heads. So in that case, I would say the probability of heads was 0.8. Classical is if everything is equally likely to occur, so fair coin, equally likely to get a head or tails, we would expect the 1 over 2. Law of large numbers, we know that the more times we flip it, the closer to one another those probabilities would be. As we do it more and more often, the empirical will look like the classical. All right, so suppose a fun-sized bag of M&Ms contains 9 browns, 6 yellows, 7 reds, 4 orange, 2 blue, and 2 green. Suppose the candy is randomly selected. What is the probability that it's yellow? Why don't you guys try this one on your own? We've done one similar already. I think you guys can do it. So how many pieces of candy do we have?
30.
30 total. So this is a classical probability because you didn't draw the candies out of the bag and then look at what happened. We know there's 30 pieces of candy. We know 6 of them are yellow, so the probability of yellow, 6 out of 30. So you could say 1/5 or 0.2. The next one, probability of blue. There are 2 blues out of the 30 candies, so you could say 1 in 15, or if you gave me the decimal, that's what, 0.0667, is that right? So, what comment could you make on this?
You're 3 times more likely to get a yellow than
Mm-hmm. All right. Any questions? What's the probability of getting a purple? 0. What do we call that? Impossible event. Okay.
I'm gonna find purple. Yeah. I'm looking for purple.
Okay. Last 2. Sophia has 3 tickets to a concert. But Yolanda, Michael, Kevin, and Marissa all want to go with her. To be fair, she randomly selects 2 people. So what would be the sample space? We pick 2 people at a time. Can I abbreviate these?
Yes.
So my options, you could get Yolanda and Michael, or we could have Yolanda and Kevin, or Yolanda and Marissa. You could have Michael and Kevin, Michael and Marissa. You could have Kevin and Marissa. And that would be it. Do I need to, does order matter on these? No. It's not like somebody's getting a really good seat and somebody's getting a bad seat. That we're just going together. So that would be our sample space. So the probability that Michael and Kevin attend. So how many options have Michael and Kevin? 1 out of how many total? So there's a 1 in 6 chance that Michael and Kevin go. What's the probability that Marissa gets to go? So how many options have Marissa? 3 out of 6. So that would be a 1/2, 2, or 0.5, or you could say 50%. So if I ask you to interpret the probability, that's just writing a sentence there, is a 50% chance Marissa attends. Marissa is chosen. Okay. So the sample space can be helpful in looking at all the different options to find those probabilities. Last actual example here. A survey asked 500 families with 3 children the gender of their children. It was found that 180 had 2 boys and 1 girl. So if I want the probability of having 2 boys and 1 girl using the empirical. Empirical is what actually happened. So that would be what? How would I find it? And what's that give us? 0.36. Okay. Compute and interpret the probability of having 2 boys and 1 girl in a 3-child family using the classical method, assuming boys and girls are equally likely. So to do the classical method would mean we have to write out all the different possibilities. Okay, and we can do it different ways. We can do just like we did the last one. We could kind of draw a diagram. Do you guys have a preference? Diagram? Okay. So This is called a tree diagram. You don't have to do it this way, but you certainly could. Alright, this program doesn't work very well with my new board, but I didn't get this file converted into a new type, so we're using it. Okay, so first child. It could be either a boy or a girl. We agree with that? And we have 3 children, so we have to keep working here. So then the next child. From each of these options, you could either have a boy or a girl. So this is the second child. So then we have 3 children, so we would have to add another set of branches. You guys understand where I got these? So this is the first child, second child, third child. So if I look at this, how many options are there? 8 total options. Okay. I want to know how many of those options have 2 boys and a girl. So it could go boy, boy, girl. It can't go boy, 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 because we need 2 boys and 1 girl. So it could go boy, girl, boy. Girl, boy, boy. Can it go girl, girl? No. So there are 3 of the 8 options that work here. And you can leave it as a fraction. If you did a decimal, you get 0.375. So we can see they're not exactly the same, but they're not too far off. And if we had a larger sample, they'd probably be even closer. Any questions there? All right, so last thing, I don't really have any examples of this, but just the last type of probability, it's on the same slide with the empirical and classical. That's subjective, where it's really based on personal judgment. So that might be an economist predicting a 20% chance of a recession next year. Okay, that is their personal opinion. If you talk to 2 different economists, you're probably going to have 2 different percentages. Can you think of any other subjective probabilities that we see all the time? Weather. You're looking at the probability of rain. Does every weather station have the exact same chance of rain? No, because there's a little bit of subjectiveness there. It kind of depends on the person. Okay, so I am done. I'm going to give you guys time to work. If you look in the book, most of the problems it says find and interpret the probability. You do not have to interpret on any of them. So if that's the only thing the question asks and interpret, but if the question says find and interpret the probability, all you have to do is find it. And we will be using our books tomorrow.